All right, recording, rolling. It is Tuesday, January 30. So we're solving puzzle update today. Yeah, you guys got your notebooks up, ready to go. And I've got some FRQs lined up for later this week, and I'll get you guys a repeat quiz by the end of the week too. All right, so that first one. Okay. Let's do. I'm drawing this with you guys so that you guys have time to follow along with me here. You guys remember there was a projectile lab that we did involved. You guys took those blaster cannons, you aimed them horizontal at the edge of that balcony, fired at some speed, right? You can call it speed blast. I might just call it V sub X because I'm aiming at horizontal. So I guess that would be the same all the way across, giving you guys some hints here. Okay? And then you guys measured what was the height drop of the balcony, and you guys measured what was this horizontal displacement from the edge of the balcony for the ball wing. Right, so that would be. Right. Let's say you're also allowed to know gravity field. Right, so we will call it G. Right, gravity field. Right. Right. So if you have this measured. This is measured, right? And then G you're allowed to know, so I'll say known. Right? Can you solve for the blast speed of the cannon, right, in terms of variables? Okay, so go ahead, right? Give you guys a head start. You guys go ahead and solve that. All right. I'll pause this video while you guys are getting a head start there. All right, if you watch this video at home, do a little time jump. You guys been solving this a few minutes. All right, so hopefully some of you guys have at the end like V sub X or V blast equals. You have an expression in terms of these measured or known variables. Okay. Who has the answer? Who knows? What is the blast speed? What's the blast speed? Who's got it? Right, everybody got it? Distance on the square root of V over 2. Right. Oh, okay, yeah. Sounds like Gavin got it. All right, everybody else get what Gavin got? Yeah. All right. All right. Joe got it. All right. Okay. Yeah. Some of you guys are getting this. Great. All right. So, what's here? I've got 2 posters I'm going to throw up here as kind of answers. So here's a big picture. This is a good place to start, right? Good place to start, right? Again, this ball is going to follow a parabola path, right? And it's going to go across the field at constant velocity, right? That's this right here, which ultimately what you're solving for, right? Okay. So how far it goes across horizontal displacement is how fast it's going across times however much time it's falling for, right? Okay. But that time that it's falling for, well, that's constrained by vertical information, right? So how tall is the cliff? The taller the cliff, the further it's going to fall, you know, how more seconds. But also the gravity field, which is also a vertical concept. So really, you need to start with vertical, right? So I would start by saying, here, this is gonna be like a 2-part problem. I would say first start with vertical, right? And I would do, if you do the full version, you could do, maybe we'll call it Y or H. Maybe scratch that, call it H. H equals V naught in the Y direction, T plus 1/2 GT squared. Okay? If down is positive, the top of the balcony is 0.0, down is positive, so that's positive, G is positive, you know, all the way positive. Right? Right? Oh, but you know what? You can actually use a simplified version of this. You don't need to use the full equation with all 3 terms, right? Guys, how can we simplify this? I can get rid of one of these 3 terms. Which one doesn't even matter? This right here, right? Because guys, if you blast it straight horizontal, then right as the ball is leaving this cannon barrel, how fast is it moving up and down? 0. Well, that's what this is. The initial in the Y direction. That's just ends up being 0 for this particular setup. Now, if you aim the cannon like 30 degrees up, okay, well, now you need the full thing, right? Okay. But this particular setup, this just goes away. Okay, okay, so it just boils down to this. H is 1/2 GT squared, right? Okay. Maybe some of you guys just went straight to that. Okay. In fact, I think if you get asked this exact question as an FRQ and you start with just that, I'm pretty sure they would give you credit. Okay, yeah, right. So you're good. Right. Right. Oh, no, what are, I know there's no numbers on here. It's all in terms of variables, right? But which one of these variables, and I see three, right? H, G, and T. Which one are you kind of solving for at this point? T, yeah, right? Because if only we knew the time of fall based on the measured balcony height and the known gravity field, right? Then we can take that now, solvable time of fall, and we can switch over to horizontal and then solve the rest of it, right? Right. So go ahead, do the algebra before I write it. Okay. So we get T equals something. Yeah. Set that much anyway. T equals what? All right, so hopefully everybody has by now. Okay. Cross multiply the 2, divide down the g, take the square root. There's a few steps in there, but you're gonna end up at this point, right? Okay. Right. That's the first half of this puzzle question. Okay. Now we're gonna switch over to horizontal. Horizontal. Okay. Okay. Horizontal. What expression should I write right here? D equals v sub x times t, right? Right. I don't need anything about acceleration. I guess the full equation would be kind of like this one again, right? But this time there's no acceleration horizontally, right? Gravity doesn't pull horizontally. We've been ignoring air drag, we usually do, right? So it's just us, right? If you're just watching it go across the speed pretty much, right? And the whole question we're solving, okay, we're trying to solve for this right here, right? This is the ultimate goal. Is that? Right? And D, this landing distance could be a measured value. Right? You guys did that a few months back. Right? You guys did. Some of you guys had meter sticks. Did you guys have the trundle wheels also? Do you guys have the trundle wheels? Yeah. Okay. Yeah. Right. That was another way you can measure D. Right. Right. Just roll it out 1 meter at a time. Right. But look at this expression for T right here. You guys take that right there. Right. Now, since you're solving for v sub x, which is the horizontal component of velocity, but it's also the velocity. It's velocity horizontal. Right? You just take T and divide it down. Okay. So v sub x is, see, the horizontal displacement divided by this expression. Right? And if you like, okay, we got a fraction within a fraction, so you could take the denominator fraction and flip and multiply it. Okay. That's what Gavin said to do too. Right? So do that times g on 2h. Like that. Like that. Right. There you go. That's the answer. Okay. So now you go to the edge of any balcony, and as long as you aim the cannon horizontal, right? Say, okay, what's the height of the balcony? Grab that, bam, right there. What's the landing displacement? Bam, right there. Right? And, you could even switch planets if you wanted to, because there's the G. Take care of that T. Blah blah blah. Right, guess that.
Chaperones going to FIT, please report to the front office by the attendant. And then please release all freshmen that are attending the FIT field trip to the attendant side of the front office. Thank you.
All right, and there's the poster version of it right there. Boom, just like that. Right, so step 1, step 2, put it all together. Okay. All right, so you guys know another class of questions AP likes to ask are proportional questions. So how about this? What if you have different cannons that blast different speeds, right? You want to compare, right? And one cannon blasts 4 times the distance, both say equal planets and equal cliffs, right? But like this horizontal displacement right here, one cannon blasts 4 times as far. If it's 4 times as far, what is the relative blast speed? 4 times as much, right? Right? Because that's a direct relationship right there, right? So I'll call that a linear relationship, direct relationship, right? 4 times here is 4 times here, right? What about this, right? What if you're comparing, again, 2 different cannons, 2 different blast speeds, but this time we got 2 different cliff heights. And let's say the ball lands exactly the same location, right? So they land like pretty much on top of each other, right? But one cliff is 4 times the height of the other cliff, right? 4 times the height of the other cliff. Right? As the cannon that's way up on the super tall cliff that's 4 times as high, what is its relative blast speed? Half as much, right? right? How do you know half as much? Exactly. Yeah. Square root denominator. Right. Put a factor of 4 on that h. Right? Here, I want to draw that one out too, right? Because maybe help see this picture. If we had two cliffs, right? I have like a short cliff and a tall cliff, right? So my picture's not exactly to scale, but you guys can get the idea, right? Suppose this is height h and this is height like 4h, right? H and then 4h, right? Right. And you got a couple of cannons, right? Blast, this one, blast, right there. This one, right there. So the cannonballs pretty much lay on top of each other, right? Yeah, the one super tall cannon not blasting as fast, right? Okay, it's some kind of that's why it's denominator. Right. And then all right, how about this? What if it's the same height cliff and the cannonballs land at the same position, but we're comparing like two totally different planets, right? So what if one planet has 4 times the gravity field, right? Well, guys, if it's 4 times the gravity field, does that cannon to hit the same spot have to be blasted not as fast or way faster? It better be way faster. Hopefully that makes intuitive sense because gravity's pulling it down in a hurry, right? So for it to land in the same spot, better blast it real fast, right? In fact, how many times as fast? If it's 4 times the gravity field, how many times is this blast speed? Twice as fast, right? Right? Because you throw on a factor of 4 on that g, right? The fact that it's under a square root, you have to blast twice as fast to hit the same spot. Okay, right, guys, see that? All right, there you go. That's all a bunch of AP skills right there. I want to do another question related to the same scenario. Right. Let's do a couple of graphs here. A couple of graphs. Side. Right. Let's call the top of the cliff 0.0, and then down is the positive direction in the vertical. Okay. And then call across the field positive direction horizontal. Okay. Let's do v sub x versus t and v sub y versus t. Okay. Yeah, for that scenario. This could be for blast, cannonball, horizontally from edge of cliff. So here's your scenario, a couple of graphs. What are those graphs gonna look like? Hoping everybody gets both of those graphs correct. Okay, everybody's got to get both of those graphs correct. V sub x versus t, v sub y versus t. Oh, maybe I should label units. Okay. Guys, what unit goes on this axis?
Meters per second.
Meters per second. How about this axis? Yeah, meters per second. All right, so okay. How about this axis? Seconds. Oh yeah, and seconds. There you go. Okay. Variable unit. Instead of like put down hash marks and start plotting specific points. Okay. Get some units there. All right. Okay. Take a quick trip around the room, see who's got these graphs. All right. Okay. I think some of you guys got the graphs. Pretty close. Pretty close. Right. Okay. So, v sub x versus t. Looks like more of you guys got this one. Right. See a lot of you guys. What's the answer to that? What should v(x) versus t look like?
Line.
Yeah, just a flat line, right? So it's not changing. That'd be a constant value, right? So you're watching like if you're up in a balloon looking down on the whole situation, looks like the ball's going pretty well constant speed across the field, right? And we just did a bunch of math to solve for that blast speed. That's also the blast speed too, isn't it? Right. All right. So then going around, looks like this one was a little trickier. Who feels like they're pretty confident about what this v sub y versus t should look like? Yeah. There you go. Right. So here, when the cannonball was leaving the cannon barrel, how fast is it going strictly up and down right at the moment it's leaving? 0 meters per second. So at time 0, it's leaving the cannon barrel, it's going 0 meters per second. 0, 0 is a single point on the graph, right? And then the rest of the graph looks like what shape? Yeah, straight line, right? With a constant slope. Right? In fact, what physical property does that slope represent?
Acceleration.
Yeah, acceleration, vertical acceleration. Call it like G for gravity field if you like. Acceleration, right? Make an equation with that. I'll v in the y direction equals v not in the y direction, which happens to be 0 meters per second, right? Plus gt, like that. Like y equals mx plus b kind of thing. All right, you guys go there. All right. Let's go to the edge of a cliff and well, guess we're at the edge of a cliff, right? Let's modify this a little bit. Right. Let's say you're gonna blast the cannonball at some angle. Blast the cannonball at some angle. Right. Let's make some graphs for this. Right. So cannon, edge of a cliff. Right. Maybe I'll blast it up at 60 degrees from the horizontal. Right. So this could be 60 degrees. Okay. Oh, so V blast. V blast. Right. And then cannon's going to cannonball is just something about like that. Okay. Right. So let's do 3 graphs. 3 graphs here. Right. I'll make this like about like sideways T looking axes. How about that? Okay. So let's do what is the height? Maybe I'll call it. How about y in terms of t? So meters, seconds. Right. What is velocity in the y direction? Meters per second as a function of time and seconds. And what is the acceleration? Let's say vertical acceleration. So that's the only way to be accelerating anyway. Okay. Maybe it's probably as a function of time and seconds. Okay. Go ahead and make those 3 graphs. Oh, and let's call down is the positive direction. Positive direction. Right. Could be either way. You could call it positive. That'd be okay too. The graphs would just flip vertically. Right? But just have let's all have the same answer here. So down is the positive direction. What do those 3 graphs look like? Gonna pause this video, give you guys another minute here. All right, recording resume, did a time jump. So I've given you guys a bunch of scenarios like this, and this should look familiar, right? There's 3 graph setup, right? This is first time, velocity first time, acceleration first time. Okay. So going over those solutions, I usually start with v versus t and then branch out. Right now, all these graphs are related to each other. If you know one, you can kind of figure out what the other ones look like. Right? Maybe especially if you're in calculus, think about how you guys are. Right? There's definitely a calculus relationship between 2 graphs. Right? So velocity versus time. What does this graph look like? What do you guys get? Aha, all right, yeah. I think Derek got it right. Yeah, I saw your paper too. You got it right. Okay. So if I'm calling down the positive direction, notice I'm strictly focused on these graphs on the vertical type motion, right? So the fact that you blast it straight upwards, isn't that in the negative direction, right? So that would have to be this point, right? In fact, could you call that, how could you calculate this exactly? This would be v blast multiplied by what? Sine of 60 degrees. Ah, right. What is sine 60 degrees? Oh, like square root 3 over 2. Yeah, right. And then, yeah, at least a diagonal up from there, something like this. Okay. And what would the slope of that line represent?
Gravity.
Yep, gravity field. Okay. Ooh, what does this point right here represent?
One's at the top.
Ah, yeah. Well, it's right at the top, right there. Boom, it's right there. Right? Okay, so that would correspond to the peak time. Right? How about this? What does the area of that there triangle represent? I just hashed it in. What does the area of that triangle represent? Yeah. Yeah, exactly. Yeah, it's this height change right here. It's vertical displacement. Right. So the area under v versus t, or between v versus t and the time curve, time axis. Yeah, it's height change right there, right? Ooh, guys, is that triangle hashed in right there about equal to there that hashed in triangle right there? Right. And if you take that negative area plus that positive area, that has to sum to what? 0, 0, right? If they're like the same size triangle, okay. Which would mean 0 displacement at this time. Is that right? Zero vertical displacement. That's right, because that's when it's bam, like right there, equal to the same height that it started at. Right? Wouldn't that be 0%? Okay. All right. How about this? Let's do A versus T. What does that graph look like? Horizontal line, okay, with a horizontal value of, yeah, say 9.8 meters per second squared, probably. Right? Yeah, a lot of these are applied. You might be on Earth. Let's call it G, more generic. Right? Gravity field. So it's over that line, isn't it? Okay. Right. And finally, Y versus T. Right? Now here's where you could define the top of the cliff to be any particular location. Have you guys, and I know, have you guys in calculus? Have you guys done integration? Yeah, you're starting on that?
Pardon the interruption. We are still missing a few freshmen for the field trip. If you brought back a permission form, please report to the front of the school. The buses are gonna roll out in 5 minutes.
Buses will leave. So if you guys did integration, you guys did the integration where at the end you say like plus C, right? Right. You guys know what I'm talking about, right? Right. So what that means is I could define the top of the cliff as like some crazy vertical height. I could also define the cliff as top of the cliff as 0.0, which in this class I usually do, and I'm going to go ahead and do that here, right? But you don't have to, right? If you define the top of the cliff as like way up there, well, see down's positive. You could put this point, this vertical intercept in where you want to, and make sense of it. Right, that's what like the plus C is, right? I'll put the top of the cliff at 0.0. Right? Right, so starting from that point, what does the rest of this graph look like? Like, how about this? I bet this is gonna be parabola, right? Parabola. Right. The fact that down is positive is gonna be a upwards parabola or downwards parabola. Upwards parabola, yeah. Right. And the vertex of the parabola is going to align with the peak height. In fact, there's actually 2 parabolas on this paper, right? There's the like physical motion of the cannonball that I sketched out here on the dash line, and there's this graph. Right? Could you take one of these parabolas, dunk it upside down, and kind of stretch it around, and it would match exactly? Like these 2 parabolas could be the exact same shape. Yeah. I mean, they're both parabolas, right? You can do with any parabola, you just kind of stretch it, you can warp it until it matches, right? Okay. Right? Guys good there? Okay. All right. So I'm going to switch over to some AP multiple choice questions. What we're going to do